The silent night sky hides a terrifying possibility that a single great barrier awaits every advanced civilization, and we may be fast approaching it. Tonight, step outside and find a dark spot away from the city lights. Then look up. Our Milky Way galaxy contains between 200 billion and 400 billion stars, and the observable universe holds roughly 2 trillion galaxies. Astronomers estimate there are 10 times more stars out there than grains of sand on all of Earth's beaches and deserts combined, roughly 100 sextillion stars, a number so large it loses meaning. Even if a tiny fraction of those stars host planets, and a tiny fraction of those planets develop life, and a tiny fraction of that life becomes intelligent, the galaxy should be teeming with civilizations. The mathematics suggests we should have neighbors, lots of them. When we point our radio telescopes at the sky, we hear nothing. When we search for alien megastructures, we find nothing. The cosmos is vast beyond comprehension, ancient beyond imagining, and utterly, eerily silent. Scientists call this the Great Silence, and the Great Silence poses what may be the most disturbing question in all of science. During the summer of 1950, physicist Enrico Fermi asked that question over lunch at Los Alamos National Laboratory. Where is everybody? Given the age of the galaxy and billions of stars, alien civilizations should have had plenty of time to make their presence known. So where were they? Fermi's question became known as Fermi's paradox. The numbers scream that intelligent life should be everywhere, and the evidence screams that it is nowhere. Economist Robin Hanson proposed an answer in 1996 called the Great Filter. The Great Filter is a nearly insurmountable barrier somewhere on the path from lifeless matter to spacefaring civilization, a barrier so deadly that virtually no species ever makes it through. Even with billions of planets rolling the dice across billions of years, almost nothing gets past the Great Filter. The chilling question is simple. Where is the Great Filter? Is the Great Filter behind us, in our past? Or is the Great Filter still ahead, waiting in our future? If the Great Filter is behind us, that is good news, because it would mean humanity is an extraordinarily rare survivor, and the road ahead might be relatively clear. If the Great Filter is ahead of us, the implications are horrifying, because it would mean civilizations routinely reach our level of technology and then destroy themselves, that we are approaching the same cliff that claimed every civilization before us. Philosopher Nick Bostrom put it this way: either we are incredibly lucky or we are doomed, and we do not yet know which. If you find this kind of deep exploration valuable, please consider subscribing and pressing the like button. It helps more than you might think. Now, let us begin. To understand why the Great Filter matters, you first need to understand the scale of what we are dealing with. The numbers involved are so large that our minds struggle to process them, but let me try to put them in perspective. The Milky Way galaxy, our home, spans somewhere between 170,000 and 200,000 light-years across. 1 light-year is the distance light travels in a single year, moving at roughly 299,792,458 meters per second, approximately 186,282 miles per second, which works out to about 5.88 trillion miles, or 9.46 trillion kilometers per light year. 1 quintillion miles from edge to edge, That is roughly how far the Milky Way stretches. Within this vast spiral structure, our galaxy contains between 200 billion and 400 billion stars. Current estimates suggest that the average star hosts at least one planet, and many stars have multiple planets. The Kepler Space Telescope and its successor missions have confirmed over 5,500 exoplanets as of 2026. With thousands more candidates awaiting confirmation and extrapolating from these discoveries, astronomers now believe there are tens of billions of potentially habitable planets in the Milky Way alone, worlds that orbit in the so-called habitable zone, where temperatures allow liquid water to exist on the surface. Now expand your view beyond our galaxy. The observable universe, the portion of the cosmos whose light has had time to reach us since the beginning, spans approximately 93 billion light-years in diameter. Within that sphere, astronomers estimate there are roughly 2 trillion galaxies. And if each galaxy contains hundreds of billions of stars, and each star may host planets, the total number of worlds in the observable universe is beyond astronomical. And this is where the paradox bites. Given these numbers, even extremely pessimistic assumptions about the probability of life should still produce millions of civilizations. Let me walk you through a simplified version of the mathematics. Suppose only 1% of stars have planets. That still leaves billions of planetary systems in our galaxy alone. Suppose only 1% of those planets are in habitable zones. Still millions of potentially habitable worlds. Suppose only 1% of habitable worlds actually develop life. Hundreds of thousands of life-bearing planets. Suppose only 1% of life-bearing planets produce intelligent life. Thousands of intelligent species. Suppose only 1% of intelligent species develop technology capable of interstellar communication. Even then, you would expect roughly 2,000 technological civilizations in the Milky Way. These are extremely conservative estimates, and they still predict that we should not be alone. The actual numbers could be far higher. Now consider time. The Milky Way galaxy is ancient, with the oldest stars in our galaxy exceeding 12 billion years in age, and our Sun, by comparison, is only 4.6 billion years old. Other star systems have had billions of years of head start on us. If a civilization arose around one of those older stars, even 1% earlier than humanity, that is roughly 130 million years ago, they would have had an incomprehensibly long time to develop technology, spread across the galaxy, and make their presence known. How long would it take for a determined civilization to colonize the entire Milky Way? Robin Hansen calculated that even at a relatively modest fraction of the speed of light, self-replicating probes or generation ships could hop from star to star and fill the galaxy in less than 100 million years. And some estimates suggest it could happen in as little as 1 million years. 1 million years sounds like a long time from a human perspective, but cosmically, it is nothing. If the Milky Way were a single year old, 1 million years would be less than 5 minutes of that year. The galaxy has had enough time for civilizations to colonize it many times over, and if even one species had gotten a modest head start, they could already be everywhere. Everywhere we look, we see nothing. No signals, no probes, no artifacts, no megastructures, no evidence whatsoever that anyone else is out there. This is the great silence, And this is why the great filter must exist. Something is preventing civilizations from reaching the point where they become visible on a galactic scale. Something is stopping them cold, and the question is what? American astronomer Frank Drake attempted to quantify the problem in 1961. Frank Drake was preparing for a conference at Green Bank, West Virginia, where scientists would discuss the possibility of detecting extraterrestrial intelligence. And to frame the discussion, Drake wrote an equation, not to solve, but to organize our ignorance. The Drake equation estimates the number of detectable civilizations in our galaxy. The equation looks like this: n equals r star times f sub p times n sub e times f sub l times f sub I times f sub c times l. Let me explain what each variable represents. N is the number of civilizations in our galaxy whose electromagnetic emissions are detectable, and this is what we are trying to estimate. R star is the average rate of star formation in the galaxy, measured in stars per year. F sub p is the fraction of those stars that have planetary systems. N sub e is the average number of planets per star that could potentially support life, essentially the number of planets in the habitable zone. F sub l is the fraction of those potentially habitable planets where life actually arises. F sub I is the fraction of life-bearing planets where intelligent life develops, creatures capable of building civilizations. F sub c is the fraction of intelligent civilizations that develop technology capable of releasing detectable signals into space. L is the average length of time that such civilizations remain detectable, their longevity. What this equation tells us is a probabilistic framework that multiplies factors from astronomy, how many stars and planets exist, through biology, how likely is life and intelligence, to technology, how likely is communication, and how long does it last. The Drake equation formalized the Fermi paradox discussion and highlighted which bottlenecks are most uncertain. When Frank Drake first presented this equation, many scientists were optimistic. Carl Sagan, the famous astronomer and science communicator, believed that the galaxy was likely filled with intelligent life, and Sagan assumed that wherever conditions allowed, life would arise, and wherever life arose, intelligence would eventually follow. Under these assumptions, the Drake equation predicted tens of thousands of detectable civilizations. And here is the problem. More than 60 years have passed since the Drake equation was formulated. During that time, SETI, the search for extraterrestrial intelligence, has listened to millions of star systems. Projects like Breakthrough Listen have scanned thousands of targets across broad radio frequencies using instruments sensitive enough to detect Earth-level transmissions from dozens of light-years away. The searches have found nothing, zero confirmed signals, and the great silence persists. This forces us to reconsider the assumptions. If n appears to be zero, or close to it, then one or more of the factors in the Drake equation must be extraordinarily small, and something in that chain of probabilities must be dropping the final answer to nearly nothing. This is where the great filter enters the picture. The great filter corresponds to at least one term in the Drake equation being so vanishingly small that it overwhelms all the others. Either life almost never arises, meaning F sub L is near zero, or intelligence almost never develops, meaning F sub I is near zero, or civilizations almost always destroy themselves quickly, meaning L is very short, or some combination of these. Robin Hansen analyzed the chain of steps required to go from dead matter to a galaxy-spanning civilization. Hansen identified roughly 9 critical transitions: the emergence of a habitable planet, the origin of self-replicating molecules, the development of simple, single-celled life, the leap to complex cells with nuclei, the development of multicellular organisms, the emergence of intelligent tool-using animals, the creation of technology, the survival of that technology long enough to become spacefaring, and finally, the actual expansion across interstellar distances. Each of these steps could, in principle, be a filter. Each could be a bottleneck where most species fail. The Great Filter hypothesis suggests that at least one of these steps is not just difficult, it is nearly impossible, with the probability of passing through it being so low that even with trillions of planets and billions of years, essentially no one makes it. Hansen's analysis suggested that to explain the observed emptiness of the galaxy, each hard step might have only about a 1% chance of success in 30 billion years, or each such step takes on the order of tens of billions of years on average to happen. This aligns with the sobering observation that in our galaxy's 13+ billion year history, not a single civilization, as far as we can tell, has reached the stage of expanding visibly across the stars. Pause for a moment and let that sink in. In all that time, across all those stars, no one has made it. Or if they did, they vanished before leaving any trace. If the Great Filter lies behind us, what might it have been? Scientists have identified several steps in Earth's history that could qualify as extraordinarily improbable bottlenecks. The first and most fundamental candidate is the origin of life itself, a process scientists call abiogenesis. Life on Earth began roughly 3.5 billion years ago, perhaps even earlier, with the earliest confirmed microbial fossils dating to approximately 3.5 billion years before the present. Despite decades of research, no scientist has successfully created life from non-living chemicals in a laboratory. Experiments like the famous Miller-Urey experiment in 1953 demonstrated that simple organic molecules, including amino acids, can form spontaneously under early Earth conditions. But amino acids are a long way from a self-replicating cell. Nick Bostrom noted that attempts to create life from scratch in the laboratory have failed to get much beyond a few simple amino acids, and no instance of abiogenesis has ever been observed. This raises a question. Was the origin of life easy, something that happens wherever conditions are right? Or was the origin of life a 1 in a trillion fluke, a cosmic accident that happened only once in the observable universe? If abiogenesis is the Great Filter, it would explain everything. Simple life would be extraordinarily rare, complex life would be even rarer, and intelligent life would be essentially unique. The silence of the cosmos would make perfect sense, because there is no one else out there, because no one else ever got started. A second candidate filter lies in the transition from simple prokaryotic cells to complex eukaryotic cells. For roughly 2 billion years after life first appeared on Earth, nothing much happened in terms of complexity, and single-celled organisms without nuclei dominated the planet. Then, around 2 billion years ago, something remarkable occurred. A prokaryotic cell engulfed another cell, and instead of digesting it, the two formed a symbiotic partnership. The engulfed cell became the mitochondrion, the powerhouse of the cell. And this merger created the eukaryotic cell, a far more complex and energy-efficient form of life. This event appears to have happened only once in Earth's history. All complex life on Earth, every animal, plant, fungus, and protist descends from that single merger, and the fact that it happened only once, despite billions of years of opportunity, suggests it may be extraordinarily improbable. A third candidate filter involves the transition from single-celled life to multicellular organisms. For another billion years or more after eukaryotes emerged, complex multicellular life failed to appear. And then, around 600 million years ago, multicellular animals suddenly appeared in an event scientists call the Cambrian explosion. What triggered this transition remains poorly understood, and it may have required specific environmental conditions, specific genetic innovations, or simply a great deal of luck. A fourth candidate filter is the emergence of intelligence capable of technology. Countless species have existed on Earth over the past 3.5 billion years, and the vast majority went extinct without producing anything remotely resembling civilization. Only one lineage, ours, developed the capacity for abstract thought, language, and tool-making at a level sufficient to build rockets and radios. Is intelligence an inevitability given enough time? Or is intelligence a rare accident, a path that almost never happens? I remember the first time I truly grasped the implications of this question. I was reading about the Burgess Shale, a fossil bed in the Canadian Rockies that preserves creatures from the Cambrian period, and the organisms in that ancient sea were bizarre beyond imagination. Five-eyed predators, creatures with bodies like accordion tubes, animals whose basic body plans went extinct and left no descendants. Looking at those fossils, I realized that 99.9% of all species that have ever existed are gone, vanished without a trace, and yet somehow we are here. The improbability of our existence is staggering. We stand on the shoulders of survivors, an unbroken chain stretching back billions of years through extinctions and catastrophes and bottlenecks, and that we exist at all may be the greatest fluke in cosmic history. If any of these past steps was the great filter, then humanity has already passed through the most dangerous bottleneck, and the road ahead might be difficult, but it would not be impossible. We would be the rare winners in a cosmic lottery, and our future would stretch out before us like an open highway. But what if we have not passed the great filter? What if the deadliest barrier still lies ahead? If the great filter is ahead of us, it means that civilizations routinely reach our level of technological development and then, almost without exception, perish. What kills them? Scientists and philosophers have proposed several candidates, and some of them hit disturbingly close to home. The first and most obvious candidate is nuclear war. Humanity split the atom in 1945 and detonated the first nuclear weapon in the New Mexico desert, and within 3 years we had used nuclear bombs on Hiroshima and Nagasaki, killing approximately 200,000 people. Within 2 decades, we had stockpiled enough nuclear warheads to destroy human civilization many times over. At the height of the Cold War in 1986, the global nuclear arsenal reached approximately 70,300 warheads, representing enough explosive power to annihilate human civilization many times over. The United States and the Soviet Union came terrifyingly close to using those weapons during the Cuban Missile Crisis of 1962. And we now know that the crisis was even more dangerous than people realized at the time. The physics behind nuclear weapons is described by what may be the most famous equation in all of science. Albert Einstein published his formula in 1905 as part of his theory of special relativity, E equals mc squared. In this equation, E represents energy measured in joules, m represents mass measured in kilograms, and c represents the speed of light in vacuum, approximately 3.0 times 10 to the 8th meters per second, or about 186,000 miles per second. What this equation tells us is that mass and energy are interchangeable. A small amount of mass can be converted into a tremendous amount of energy because c squared is an enormous number. If you could convert just 1 kilogram of mass entirely into energy, you would release approximately 9 times 10 to the 16th joules, that is 90 quadrillion joules. For perspective, the largest nuclear weapon ever detonated, the Soviet Tsar bomber at 50 megatons, released approximately 2.1 times 10 to the 17th joules by consuming only a few kilograms of mass. This equation underpins both the stars and our bombs. In stars, mass is converted to energy through nuclear fusion, allowing them to shine for billions of years. In human civilization, this same principle enabled nuclear weapons and nuclear power. A nuclear fission bomb converts only on the order of grams of mass into energy, yet that conversion can destroy an entire city. The great filter ahead might very well be tied to this equation. As soon as a civilization taps relativistic energy, it gains the ability to obliterate itself, and our first use of E equals mc squared in warfare killed approximately 200,000 people. By the 1960s, we had stockpiled explosives equivalent to millions of Hiroshimas, and that escalation of power made possible by physics described in 1905 means any technological species might inevitably create weapons of mass destruction. Whether they use them or control them becomes a filter question. Since the end of the Cold War, global nuclear stockpiles have decreased significantly. As of early 2026, the world possesses approximately 12,300 nuclear warheads, representing roughly an 80% reduction from the 1986 peak. 12,000 warheads is still an enormous number, equivalent to approximately 146,000 Hiroshima bombs in firepower. A sobering fact, just 100 nuclear detonations on major cities could cause a nuclear winter severe enough to crash agriculture worldwide. The weapons that remain are more than sufficient to end civilization, and the United States and Russia maintain roughly 90% of these weapons, with each nation having several thousand warheads on high alert. 17 years passed between splitting the atom in 1945 and the Cuban Missile Crisis in 1962, and the first species to split the atom nearly used it on itself within that span. Avoiding nuclear self-destruction remains a key hurdle we still face. Naturally occurring pandemics have periodically killed large fractions of human populations throughout history. The Black Death killed roughly 30 to 50% of Europe's population in the 14th century. The 1918 influenza pandemic killed an estimated 50 million people worldwide. And the recent COVID-19 pandemic caused approximately 20 million excess deaths globally between 2020 and 2022. These numbers are devastating. but they are small compared to what an engineered superpathogen could accomplish. Consider a virus intentionally modified to be as contagious as measles and as lethal as Ebola. Such a pathogen could have a mortality rate exceeding 50% while spreading to virtually everyone on Earth, which could mean billions of deaths in a single wave. Pathogens represent a filter that could strike suddenly. Unlike climate change or even nuclear war, a bioengineered plague released in a major airport could circle the globe in days thanks to modern air travel, and before the COVID-19 pandemic, the world saw approximately 50 million flights per year. Our interconnectedness means disease can hop continents overnight. The COVID-19 pandemic served as a wake-up call. While the coronavirus pandemic was not an extinction-level event by any means, it demonstrated how a novel pathogen can disrupt the entire globe in weeks. On the flip side, CRISPR and gene drive technology are advancing rapidly, making engineering pathogens easier for smaller groups with fewer resources. Experts at institutions like the Future of Humanity Institute have estimated a roughly 1 to 2% annual chance of a global catastrophic pandemic in the coming decades, including both natural and engineered pathogens. The key number to watch is how quickly we can detect and contain outbreaks, because minutes and hours matter. Data and early warning systems are critical in predicting how future pandemics will spread and how deadly they could be, which will determine whether we can counter this manifestation of the Great Filter. The most fast-moving existential risk may be artificial intelligence. By 2025, cutting-edge AI models have tens of trillions of parameters and can outperform humans in many narrow tasks. The cost per computation has been dropping exponentially according to Moore's law and its successors, and the amount of computing power required to train frontier AI models has been doubling every 6 to 10 months, much faster than the doubling of hardware power itself. Some forecasts predict that by the 2030s we may have AI systems with processing power comparable to the human brain, estimated at 10 to the 15th to 10 to the 17th operations per second, running at costs that make them ubiquitous. An oft-cited survey of AI experts conducted in 2017 indicated a 50% probability of artificial general intelligence by around 2060, and a non-negligible probability, roughly 5 to 10%, of extremely bad outcomes from AI misalignment, representing another possible Great Filter. In 2023, a statement signed by hundreds of AI experts and CEOs was published declaring that mitigating the risk of extinction from AI should be a global priority alongside other societal scale risks such as pandemics and nuclear war. This single-sentence statement was signed by leading AI researchers, including Geoffrey Hinton, and by the CEOs of OpenAI and DeepMind. The seriousness with which even the creators of AI view the long-term risk is telling. Whether artificial intelligence becomes a friend or foe depends on what researchers call the evolving nature and disposition of our high-tech society and how we manage AI's integration. While there is no single statistic that encapsulates AI risk, consider this. An AI system that achieves recursive self-improvement could potentially enhance itself on a timescale of hours, far outpacing any human response. And if such a system were misaligned with human values, it might view humanity as expendable. Even a 1% chance of this outcome is unacceptable, when the downside is literally human extinction. Climate change represents a slower-burning existential risk. As of 2024, the global average temperature reached about 1.55 degrees Celsius above the pre-industrial baseline of 1850 to 1900. Likely the first time in human history we have crossed 1.5 degrees Celsius for a full year. Carbon dioxide concentration in the atmosphere now sits at approximately 420 parts per million, up from roughly 280 parts per million in the 1700s, a level not seen in at least 3 million years. Each year, humanity emits roughly 40 billion tons of carbon dioxide, and though the growth of emissions has slowed, we are not yet reducing absolute emissions meaningfully. The Paris Agreement aims to limit warming to well below 2 degrees Celsius, but current policies put us on track for approximately 2.5 to 3 degrees Celsius by 2010. Key thresholds loom ahead. 2 degrees of warming may commit the eventual collapse of the West Antarctic ice sheet, representing roughly 3 meters of sea level rise over centuries. Warming of 2.5 degrees Celsius or more could initiate permafrost carbon feedbacks that accelerate the process. The fear from a great filter standpoint is less about Earth becoming uninhabitable, because our planet will not become like Venus from human emissions, and more about societal collapse. Food insecurity, conflict, and systemic instability could derail our progress or even cause a population crash. Each degree of warming is projected to reduce staple crop yields by roughly 5 to 15% absent adaptation, while global population and demand continue to rise. Climate change unfolds over decades, which is slow enough for us to respond if we choose to do so. The impediment, as NASA researchers have noted, is that transitioning the global energy system away from fossil fuels is extremely challenging and requires unprecedented coordination. If we fail, climate stress might act in concert with other risks, pandemics, resource wars, social breakdown, to form a compounded Great Filter scenario. Earth has a long history of asteroid and comet impacts, some of which caused mass extinctions. A commonly cited statistic, the probability of a roughly 1-kilometer asteroid, global catastrophe scale, hitting Earth is approximately 1 in 500,000 per year. This is a 0.0002% chance annually, small on any given year, but integrated over millions of years, it becomes essentially certain. The Chicxulub impact 66 million years ago involved an asteroid roughly 10 to 15 kilometers in size. To understand the energy involved, we can use the kinetic energy equation from classical mechanics. Kinetic energy equals 1/2 times mass times velocity squared. In this equation, kinetic energy is measured in joules, mass in kilograms, and velocity in meters per second. Consider an asteroid 10 kilometers across with a mass of approximately 10 to the 15th kilograms hitting Earth at roughly 20 kilometers per second. Plugging those values into the equation, kinetic energy equals 1/2 times 10 to the 15th times 20,000 squared. That works out to approximately 2 times 10 to the 23rd joules, on the order of the dinosaur-ending Chicxulub impact energy. And such an impact released energy equivalent to roughly 5 billion Hiroshima bombs in a single moment. That catastrophe caused global wildfires, blocked sunlight for years, and triggered a mass extinction that wiped out the non-avian dinosaurs. The odds of another Chicxulub-scale impact are roughly 1 in 100 million per year, and given geological timescales, Earth has seen many such events. Over very long periods, the odds of a mass extinction-level impact approach 100%. Over the next 100 million years, the chance of a life-ending impact is nearly certain unless preventive measures are taken. On shorter timescales, NASA has catalogued more than 95% of near-Earth asteroids, larger than 1 kilometer, and none currently pose an imminent threat. Smaller impacts happen more frequently. The 2013 Chelyabinsk meteor was roughly 20 meters across and injured approximately 1,500 people with its airburst shockwave. Encouragingly, technology like NASA's DART mission, which in 2022 successfully deflected an asteroid's orbit through kinetic impact, demonstrates that we have the capability to intercept and nudge threats given enough lead time. With decades of warning, a deflection mission has greater than 90% chance of success against a 100 to 300 meter asteroid. Asteroid impacts, while a real natural filter, are one we might neutralize with global effort. And this makes cosmic impacts less likely to be the universal great filter, because purely random disasters would not hit every civilization without exception at the same technological stage. To understand why civilizations might face existential threats, we need to understand the mathematics of growth. Human population and many aspects of civilization, energy use, economic output, computing power, have exhibited exponential growth. The exponential growth model is described by this equation: n of t equals n0 times e to the power of r times t. Let me explain each variable. N of t represents the quantity, such as population, at time t. N0 represents the initial quantity at time 0. The letter r represents the growth rate per unit time. The letter t represents time elapsed. And e is Euler's number, approximately 2.718. What this equation describes is how a population or any quantity growing at a constant percentage rate increases continuously. The hallmark of exponential growth is that the absolute increase gets larger over time because it is proportional to the current size. If the growth rate r is positive, the quantity grows. If r is negative, the quantity decays. A useful concept related to this equation is doubling time, which equals the natural logarithm of 2 divided by r. For a growth rate of 2% per year, the doubling time is roughly 35 years. Human population has followed this pattern with stunning speed. World population climbed from approximately 1 billion in 1800 to 8 billion in 2022. An 8-fold increase in just over 200 years. At the start of the 20th century in 1900, the global population was roughly 1.6 billion, and we have added approximately 6.4 billion people in just 12 decades. This equation conveys why unchecked growth leads to explosive numbers that can quickly overshoot available resources. A classic analogy: bacteria in a bottle doubling each minute will fill the bottle suddenly, and the last doubling goes from half full to full in a single interval. Humanity's 8 billion people grew from 1.6 billion in 1900, representing an effective growth rate of approximately 1.3% per year over that period. Such growth stresses food, water, and ecosystem services, potentially triggering a collapse, a great filter scenario if limits are reached too quickly. Technology has so far extended carrying capacity, but the model points to a trap. If the growth rate stays positive and high, eventually something gives, and either the rate drops through deliberate choice or the population crashes through catastrophe. Many worry that our exponential growth in consumption and waste, carbon dioxide emissions, grew exponentially with a rate of roughly 2% for decades, could lead to environmental collapse. This equation is also relevant in nuclear chain reactions, where each fission triggers more reactions, causing exponential increase, and the equation describes pandemic spread, where early virus transmission in a susceptible population is exponential. If a civilization cannot control exponential processes, whether population growth, resource consumption, or self-replicating technologies, it might self-destruct. This represents one possible mechanism for the Great Filter. Even if a civilization survives its technological adolescence, it still faces the challenge of becoming spacefaring. The distances between stars are enormous barriers that any civilization must overcome to physically spread across the galaxy. Our nearest stellar neighbor, Proxima Centauri, is approximately 4.24 light-years away, which translates to about 25 trillion miles, or roughly 40 trillion kilometers. With current spacecraft technology, the Voyager probes travel at approximately 17 kilometers per second, and it would take roughly 75,000 years to cross just 4 light-years, essentially impractical for any meaningful colonization effort. Even at an optimistic future speed of 10% the speed of light, reaching Proxima Centauri would take 42 years. Crossing the entire galaxy, 100,000 light-years, at that speed would require on the order of 1 million years. The physics of escaping a planet's gravity is described by the escape velocity equation. Escape velocity equals the square root of 2 times g times m divided by r. In this equation, escape velocity is measured in meters per second. G is the universal gravitational constant, approximately 6.674 times 10 to the negative 11th Newton meters squared per kilogram squared. M is the mass of the gravitating body in kilograms, and r is the radius from the center of mass at which escape is attempted, typically the planet's surface. This equation comes from equating kinetic energy to gravitational potential energy, and gives the critical speed an object must have to break free from a planet or star's gravity. If an object is launched upward at escape velocity or above, ignoring atmospheric drag, it will slow down but never quite stop, eventually reaching infinite distance with 0 speed remaining. For Earth, plugging in our planet's mass of 5.97 times 10 to the 24th kilograms and radius of 6.37 times 10 to the 6th meters, we get an escape velocity of approximately 11,186 meters per second, roughly 11.2 kilometers per second, or about 25,000 miles per hour, or 7 miles per second. All our rockets must reach roughly this speed to achieve orbit and go to space, which translates to enormous energy requirements, approximately 6 times 10 to the 7th joules per kilogram of payload. This equation quantifies one natural filter. Escape in one's home planet is hard. Not every civilization might manage to go orbital if they lack abundant energy or the right technology. A planet with higher gravity would have a higher escape velocity, requiring even more powerful rockets. And if intelligent beings arose on a super-Earth with an escape velocity of, say, 20 kilometers per second, reaching space would be far more challenging, potentially stalling their expansion entirely. Overcoming escape velocity is the first step to becoming spacefaring. If a civilization cannot routinely reach this speed, it remains planet-bound and vulnerable to local disasters. All known spacefaring attempts, Sputnik in 1957, the Apollo missions, the Mars rovers, had to contend with this speed barrier. Many civilizations may never get past this hurdle before self-destructing, developing destructive technologies faster than they develop spaceflight technologies. The escape velocity equation represents the price of admission to the cosmos. Humanity achieving 11.2 kilometers per second in the 20th century was a monumental achievement. Whether we can go further, interplanetary, eventually interstellar, depends on mastering even greater velocities and doing so safely. As I mentioned earlier, 1,000,000 years is cosmically brief. If even one civilization had overcome these challenges and gotten a modest head start, they could have spread across the entire galaxy by now. The scale of the galaxy is both a daunting challenge and completely surmountable on cosmic timescales. The emptiness we observe suggests that either no one out there has even tried, or those who tried somehow failed or disappeared. To understand the scale of what advanced civilizations might achieve and why their absence is so puzzling, scientists developed what is called the Kardashev scale. Soviet astronomer Nikolai Kardashev proposed this classification system, which categorizes civilizations by the amount of energy they can harness. A Type 1 civilization on the Kardashev scale uses approximately 4 × 10 to the 12th watts continuously, that is 4 trillion watts, corresponding roughly to the total solar energy available to a planet like Earth. Humanity's current power consumption is approximately 18 terawatts, or 1.8 × 10 to the 13th watts. And by some calculations, we are currently around 0.7 on the Kardashev scale. Not quite a full planetary civilization yet. A Type 2 civilization would harness the energy output of an entire star, approximately 4 × 10 to the 26th watts. The output of a sun, roughly 400 trillion watts. A Type 3 civilization would command the energy of an entire galaxy, approximately 4 × 10 to the 37th watts. We are many orders of magnitude away from Type 2 or Type 3. The gap between our current 18 terawatts and a star's output of 4 × 10 to the 26 watts is almost incomprehensible. Why does this matter for the Great Filter? Achieving Type 2 or Type 3 status requires survival and expansion for millennia or millions of years, and it requires harnessing enormous energies safely. The Great Filter might be precisely what prevents civilizations from ever reaching Type 2. The challenges of managing planet-scale energy, avoiding climate collapse or nuclear war, may be so great that few species make it past Type 1. Consider what a Type 2 or Type 3 civilization would look like from our perspective. A civilization capable of harnessing a star's energy might build megastructures like Dyson spheres, vast constructs that partially or completely surround a star to capture its output, and such structures would alter the star's light signature in detectable ways. A Type 3 civilization that had spread across a galaxy might show up as a galaxy with unusual infrared signatures from waste heat. We see normal starlight everywhere. We see no obvious engineered spectra in nearby stars. galaxies, including our own Milky Way, look natural, physically governed by stars, gas, and black holes, not by galaxy-spanning life forms. This means any civilization that reaches those scales is either exceedingly rare or short-lived. The Great Filter perspective quantifies this absence. Not one out of billions of opportunities in our observable past light cone has reached a visible colonization stage. That is a powerful way to grasp how alone we appear to be, and it is what makes the Great Filter hypothesis necessary to reconcile expected numbers with observed reality. This brings us to perhaps the most jarring, counterintuitive takeaway of the Great Filter concept. Discovering evidence of life elsewhere could be terrifying. Normally, one would think finding alien life, even simple microbes on Mars or Europa, would be cause for celebration, a scientific breakthrough of the highest order. Nick Bostrom argues the implications run deeper. Bostrom wrote that if we discovered that life had developed independently on Mars, it must surely have happened millions of times across the galaxy, and this would mean the Great Filter is more likely still to come. Think about what this means. If life, especially complex life, is common, yet no advanced aliens are detectable anywhere, then whatever stops civilizations must act later in the sequence. The filter would likely operate at a stage we have not yet reached, or one we are just now reaching. Bostrom went so far as to say that discovering fossils of something like a multicellular creature on Mars would be, in his words, by far the worst news ever printed on a newspaper cover. This flips our intuitions completely. We want the universe to be empty of life, or at least complex life, because an empty universe implies the Great Filter is behind us, and we would be the lucky winners of a cosmic lottery. Conversely, a universe teeming with simple life means the filter is ahead of us, a doom yet to unveil itself. Bostrom famously stated that he hopes the search for extraterrestrial life finds nothing, a deeply unsettling stance because scientists are trained to hope for discovery. Yet here, the prudent hope is to find silence and emptiness. This creates an emotional paradox, cheering for a sterile solar system, finding comfort in loneliness. Few concepts illustrate such ironic dread, because the more special we are not, the more doomed we likely are. Before I tell you about current searches, take a moment to consider this. What would you feel if tomorrow's headlines announced the discovery of ancient bacterial fossils on Mars? Excitement? Wonder? Now consider, that discovery might also be telling us that our species is approaching the same wall that stopped everyone else. As of 2026, we are on the cusp of being able to detect biosignatures in exoplanet atmospheres. The James Webb Space Telescope, launched in 2021, has already characterized the atmospheres of some gas giants and smaller planets called mini-Neptunes, finding water vapor and other compounds. In the coming years, JWST and upcoming extremely large ground telescopes will target Earth-sized planets around red dwarf stars like the TRAPPIST-1 system, searching for gases like oxygen, ozone, and methane that might indicate biological activity. A confirmed detection of an oxygen-rich atmosphere on a rocky exoplanet would strongly suggest the presence of life, since oxygen is highly reactive and short-lived unless continually produced by biological processes. Such a discovery would be groundbreaking, and through the Great Filter lens, possibly ominous. The current status is that no incontrovertible biosignatures have been found beyond Earth yet. Scientists are preparing careful frameworks, like the Confidence of Life Detection Scale, to verify any claims rigorously. If in the next decade we find multiple worlds with signs of life, it will imply life is common, fanning concerns about the filter ahead. Conversely, a continued lack of biosignatures in many Earth-like targets would imply life might indeed be rare, leaning toward the filter behind us scenario. Our own solar system serves as a laboratory for understanding how common life might be. NASA's Perseverance rover, which landed in 2021, is exploring an ancient lakebed called Jezero Crater, and the rover is caching samples that will be returned to Earth by approximately 2033. Perseverance has already found organic molecules in Martian rocks, but organic molecules can form through non-biological processes too. The sample return mission, once those rocks are analyzed in Earth laboratories, will allow rigorous tests for biosignatures, isotopic ratios, complex organic structures, possible microfossil-like textures. As of now, results are pending. If those samples show definitive microfossils or cell-like structures, it would mean life started on Mars independently. Unless one argues that meteorite exchange could have seeded life between Earth and Mars, which is possible, this would suggest two independent origins in a single solar system, and that would imply life arises easily and often, which from the Great Filter perspective is concerning. Jupiter's moon Europa and Saturn's moon Enceladus have subsurface oceans beneath their icy crusts. The Europa Clipper mission, launching in 2024 and arriving around 2030, will assess Europa's habitability and possibly detect organic molecules in the ice. ESA's JUICE mission, launched in 2023, will conduct similar investigations. Enceladus is already known to spew water plumes containing organic compounds from its subsurface ocean, and future missions could directly sample those plumes for signs of microbial life. Right now, we know these ocean moons have energy sources and the necessary chemistry for life, but we have no evidence of life there yet. These are frontiers that within 20 to 30 years could answer whether a second independent origin of life occurred in our solar system. Modern SETI is far more powerful than in Frank Drake's day. Projects like Breakthrough Listen, operating since 2015, have scanned thousands of star systems across broad radio frequencies at sensitivities that would catch Earth-level transmissions from dozens of light-years away. The Breakthrough Listen initiative has also searched for laser signals, alien megastructures, and even industrial pollutants in exoplanet atmospheres. Results so far: no confirmed techno-signatures. Non-detection is not proof of absence, because aliens might use communications we cannot pick up, or they might be intentionally quiet. But after approximately 60 years of intermittent searching and roughly 10 years of intensive searching, we have zero confirmed signals. In 2020, Breakthrough Listen observed a tantalizing radio narrowband signal from the direction of Proxima Centauri, dubbed BLC-1, which passed many filters for artificiality and caused considerable excitement. By 2021, analysis revealed it was likely Earth origin interference, mimicking an artificial techno-signal. This episode demonstrates both how sensitive SETI has become and how our own noise can create false alarms. The silence continues to the present day, making Fermi's paradox stronger with each passing year. And every improvement in search capability that yields no results pushes the probability of "we are alone" or "extremely rare" slightly upward. In the 1970s, astrophysicist Michael H. Hart and physicist Frank Tipler independently argued that if aliens existed, they should already be here, not just their signals, their physical presence. Hart and Tipler reasoned that any sufficiently advanced civilization could build self-replicating probes that would travel to nearby star systems, replicate using local resources, and then send copies of themselves to additional star systems. This process, even at modest speeds, could fill an entire galaxy in a few million years, a cosmic blink. The absence of aliens on Earth, Hart and Tipler argued, implies we are likely alone or unique. This is sometimes called the Hart-Tipler conjecture. Their work sharpened the paradox. The silence is not just about radio signals, it extends to no visitation, no physical evidence, no alien artifacts or colonies anywhere in our solar system despite ample time for expansion. This underlines the need for some filtering mechanism. Either virtually no civilizations arise, or they do not expand, or they do not survive long enough to expand, and something is stopping them. A subtle, counterintuitive argument comes from what philosophers call the anthropic principle. No matter how improbable intelligent life is, we observers inevitably find ourselves on a planet where it happened. This means that just because we exist, we cannot conclude that intelligent life is easy or common. Intelligent life might be incredibly hard, a 1 in a trillion fluke, but in the hypothetical universes or planets where it never happens, no one is there to wonder about it. This reasoning cautions us not to generalize from a sample of 1. Many people intuitively think the emergence of life must be likely because here we are. The anthropic reasoning flips that logic. Observers will always observe conditions that allowed observers to arise, and we might just be the lucky lottery winners who, of course, feel it is normal to win, since those who lost the lottery do not exist to feel anything. The concept is strange and often misused, but in great filter discussions, it is vital. The silence out there combined with our existence here is perfectly consistent with life being extraordinarily rare. We should not complacently assume many others exist, and the default assumption should perhaps be that we are an exception until proven otherwise. This is a reversal of the Copernican principle, the idea that we occupy no special place in the cosmos that many scientists hold dear. The Great Filter forces us to consider that we might be uncomfortably significant. For centuries, we speculated about the plurality of worlds and we assumed mediocrity, that we are typical. The Great Filter allows for the possibility that we are astonishingly rare, perhaps the only intelligent life in our galaxy or even the observable universe, a notion hard to internalize. The numbers seem to scream otherwise, yet the silence, coupled with the filter logic, suggests a scenario where every other potential cradle of intelligence failed at some step. If true, it means the fates of 100 billion galaxies might rest on us. The very advances which empower a civilization might inevitably doom it, and it is counterintuitive and unsettling to consider. One would expect progress to be purely positive, more knowledge, more capability. History has shown that each major technological leap has a dark side. Splitting the atom unlocked nuclear power, but also nuclear bombs. Industrial chemistry gave us medicines, but also nerve agents. Microelectronics gave us global communication, but also the potential for pervasive surveillance and autonomous weapons. A NASA-affiliated paper put it this way: nearly every great discovery or invention is all too quickly turned to destructive ends. Capability breeds risk, which is counterintuitive from a naive perspective that assumes intelligence equals wisdom. Instead, we observe that intelligence often outpaces wisdom, and the great filter might simply be that by the time civilizations have immense powers, they also have immense capacity for self-annihilation, and they usually pull the trigger, whether intentionally or accidentally. As some researchers have grimly suggested, technological advancement may ultimately lead to self-destruction as a matter of course. This forces us to question the typical narrative of ever-ascending progress and consider that there might be a natural ceiling beyond which systems destabilize, like reaching critical mass and then exploding. I find myself returning to this point often. We have learned so much, and yet the deepest questions remain as open as ever. Science can describe what happens and how it happens. The question of why anything exists at all sits beyond the reach of telescopes and equations, and the question of whether we can survive our own ingenuity remains unanswered too. The term "the great filter" suggests a singular barrier, but reality might be messier. The filter could consist of an accumulation of smaller probabilities or several different fatal traps operating at different stages. Both past and future filters could exist. Maybe abiogenesis is very hard, so almost no life ever starts, and even among those few worlds where life does arise, almost none avoid eventual self-destruction. We could have passed some filters and still face others. This is counter to the neat narrative of one big filter, and it suggests the solution to Fermi's paradox might be that many things went wrong for life in the cosmos, not just one catastrophic bottleneck. Robin Hansen's analysis indicated that to explain the observed emptiness of the galaxy, the cumulative probability of any single planet producing a spacefaring civilization must be on the order of 1 in 10 to the 22nd power, 1 chance in 10 sextillion, lottery odds multiplied by lottery odds multiplied by lottery odds. The great filter, whatever it is, must be almost perfectly lethal. This is unsettling, because it means we cannot pin all our hopes on having cleared the single hurdle already. There might be more hurdles stacked ahead, and the cosmic gauntlet may be long and brutal. The great filter is an abstract concept. Let me offer some analogies that might help bring it into focus. Imagine billions of people each buying a lottery ticket every day for billions of years, and almost no one ever wins. That is the great filter. Even with countless chances across the galaxy, the ticket of becoming an interstellar civilization almost never hits the jackpot. Alternatively, picture each step toward an advanced civilization as a chamber in a revolver for Russian roulette. The great filter implies at least one chamber is loaded with a bullet, and virtually every species eventually spins it. If that loaded chamber is ahead of us, we are all playing a deadly game of chance as we progress technologically. And every advancement, nuclear power, genetic engineering, artificial intelligence, is another spin of the cylinder. Think of the universe as a giant sieve, and we are a lone grain that somehow passed through. The great filter is the finest mesh in that sieve. Trillions of grains of sand, planets, species start at the top, but the sieve only lets a vanishingly small number through to the bottom, and by the time you get to advanced spacefaring civilization, Perhaps only one grain has passed through, maybe us. The entire beach poured through successive filters, forming stars, planets, life, intelligence, technology, until nearly nothing remains. Imagine a mile-long obstacle course with 10 massive hurdles. Billions of runners start the race, but at each hurdle, 99.9999% crash and cannot continue. And even by hurdle 5, almost no one is left running. Each hurdle represents a critical step: the origin of life, development of intelligence, survival of technology. The final hurdle might be, do not destroy yourselves. The existence of even one finisher would mean we would see evidence, someone at the finish line. And the fact that the finish line looks empty suggests no one has cleared all the hurdles. We are perhaps at hurdle 8, civilization as we know it, approaching hurdle 9, becoming multiplanetary or surviving a critical technological threshold. Are we an Olympic athlete near the final jump? Or just another exhausted runner fated to collapse on the track? Envision a dark field that every young civilization must cross to reach the other side, interstellar status. The field is littered with hidden landmines, and most civilizations stepping out into it eventually trigger one and are destroyed. The survivors, if any, make it across silently, perhaps far away. We are currently tiptoeing through this minefield with nuclear weapons, CRISPR bioengineering, artificial intelligence, each potentially a mine waiting to explode. The silence we hear from the cosmos could be the stillness of a field where every other traveler has perished. This analogy highlights why even random-seeming disasters like asteroid impacts might not explain the silence. The mines that every civilization inevitably steps on are what matter. Fundamental technology, pitfalls that repeat across species, both chilling and motivating. If we can map the minefield carefully through foresight and global cooperation, maybe we can be the first to cross safely. Science fiction writer Arthur C. Clarke encapsulated the stark nature of our situation. Two possibilities exist. Either we are alone in the universe, or we are not. Both are equally terrifying. Either we stand in a fertile garden improbably alone, terrifying in its implication of looming doom if we are exceptional survivors, or the night is full of shadows of others and something is hunting them, equally terrifying. Either the universe is mostly wasteland and we are a rare exception, or it is a graveyard with one grave, perhaps ours, still unfilled. In late 2022, a team of NASA scientists, led by Jonathan H. Jiang at the Jet Propulsion Laboratory, published a paper exploring the likelihood that humanity is now approaching its own great filter. The NASA team explicitly linked the Great Filter concept to current existential threats and argued that our exponential technological advancement could trigger a disaster that wipes us out before we become multiplanetary. This marks one of the first times NASA-affiliated researchers used the Great Filter terminology in a formal scientific analysis. The idea has moved from science fiction speculation towards serious academic consideration. The Jiang paper catalogued risks including nuclear war, pandemics, artificial intelligence, and climate change. The NASA researchers urged what they called an introspection period, a time for humanity to carefully consider and mitigate these threats before they overwhelm us. The paper received considerable media attention and underscored that the concept of a civilization-ending barrier is not just theoretical, but something we must actively strive to avoid. What strikes me about this development is the shift in tone. For decades, discussions of the Great Filter existed mostly in the realm of astronomy and philosophy, an interesting thought experiment about why the sky is silent. Now, organizations like NASA are treating it as a practical concern relevant to policy decisions. The current generation might be the one to either break the Great Filter or succumb to it. Let me summarize our current position. We live in a pivotal time where we are actively searching for life beyond Earth while simultaneously grappling with risks that could end life on Earth. On the search front, the James Webb Space Telescope is analyzing exoplanet atmospheres. The Perseverance rover is caching samples on Mars for return to Earth. Future missions will explore the ocean moons Europa and Enceladus. SETI continues scanning the sky with increasingly powerful instruments. Within the next 2 decades, we may have answers about whether life exists elsewhere in our solar system or on planets around nearby stars. On the risk front, global nuclear arsenals remain capable of destroying civilization. Climate change is accelerating. Artificial intelligence is advancing at breakneck speed. Biotechnology is democratizing in ways that could enable engineered pandemics. Decisions made now about how we regulate AI, how we transition energy systems, and how we maintain global stability will shape whether we navigate the minefield or step on a mine. The next few decades, the 2020s through the 2040s, are likely to produce critical data. Either we start seeing life everywhere, which has grim implications for our future, or we find nothing, which suggests we are special but must not squander that position. The current generation might determine whether the story of the universe includes intelligent life that endures, or whether that story is just a brief flash ending in silence everywhere. Despite all our advances, science has clear limits in explaining the Great Filter and the existential questions it raises. Let me acknowledge some of these mysteries. We still cannot answer how non-living chemicals transitioned to the first self-replicating organisms. All laboratory experiments since Miller and Urey in the 1950s have shown it is relatively easy to form basic organic molecules, but extremely difficult to assemble them into a self-reproducing, evolving system. We have no consensus theory for the origin of life. The origin of life remains one of the greatest mysteries in science. Science describes the conditions of early Earth and proposes what might have happened, but why life emerged at all, and only once as far as we know, is unanswered. If life's origin requires an astronomically improbable set of coincidences that borders on territory beyond what science alone can fully address, why those coincidences happened here and perhaps nowhere else is a question that science struggles to answer definitively. Fermi's question, "Where is everyone?" remains unanswered. Science can list possibilities. They are rare, they are hiding, they are extinct. We have 0 data points of extraterrestrial intelligence to directly study. This is an observational limit. We can only detect what is detectable with our instruments and our assumptions about what signals or artifacts to look for, and perhaps advanced life is out there but fundamentally undetectable using methods we know. If so, we could be surrounded by signals or even beings and remain oblivious, like a tribe with drums unable to hear radio waves. This unknown is essentially a wall. We do not even know if our null result is because nobody is there or because we are looking in the wrong way. Until we encounter something, where are they, is as much a philosophical question as a scientific one. The fact that the simplest answer, nowhere, we are alone, could be true carries profound implications. Why would a vast universe produce one fleeting outpost of intelligence? That seems like an enormous waste of space, as Fermi himself mused. Science has no way to address why at that cosmic scale, except to acknowledge the mystery. The conditions of the universe appear remarkably suited for life in many ways. If fundamental constants, the strength of gravity, the charge of the electron, the mass ratios of particles, were slightly different, stars might not form stably, or chemistry might be impossible. Many scientists have pointed out this apparent fine-tuning. Science can measure these constants and note the results. Why those constants have the values they do is unknown. One could invoke a multiverse. Perhaps countless universes exist with different parameters, and we naturally find ourselves in one of the rare, life-friendly configurations. That is more a philosophical or speculative resolution and is not currently testable. At the limits of explanation, we confront the question, why is there something rather than nothing, and why does that something allow observers like us to exist? Science may never fully answer that question, and it might always require an assumption or leap outside the system of physical laws. How all of this came to be, why there is something rather than nothing, remains one of the deepest questions we can ask. Science can describe what happens and how it happens, but the question of why anything exists at all sights beyond the reach of telescopes and equations. I find this beautiful rather than troubling. The more I learn about the scale of what exists out there, the more I realize how small our certainties are. We do not fully understand our own emergence of intelligence and consciousness. Neuroscience can map brain activity. Biology can outline cognitive development across species. Subjective experience, why we are aware, not merely biological machines, is what philosophers call the hard problem of consciousness. If intelligence is rare in the universe, is it because consciousness requires some factor we do not yet understand? We can describe brain wiring, but why sentience arises from neurons firing remains unresolved. When asking why there are no aliens out there, one answer could be that perhaps consciousness almost never ignites. That is an intriguing and melancholy possibility that science cannot currently refute or confirm. If indeed we are the only or one of very few intelligent species in the galaxy, then something follows. The fate of cosmic awareness rests on us. This elevates our existential significance immensely. It bestows a kind of responsibility that no previous generation contemplated, the responsibility not to go extinct. Carl Sagan said that in all our searching, the only thing we have found that makes the emptiness bearable is each other. If each other extends to all of life's rarity, then preserving humanity and the biosphere we emerged from becomes enormously important in a way that transcends ordinary ethics. Philosophically, this challenges both our sense of insignificance and our tendency toward nihilism. We are not the center of the universe in terms of location or size. We might be central in importance because without us, or creatures like us, the universe would be silent and unwitnessed, a reversal. Rather than being insignificant specks, we could be the only eyes, ears, and mind in the cosmos. That imbues every human action with weight. Our wars, our consumption, our innovations, they either nurture the flame of cosmic awareness or snuff it out. Two scenarios follow from the Great Filter. If we are alone, the vast cold cosmos is entirely our stage, a sobering, lonely prospect. If others exist but are doomed never to meet us because they all perish or are too distant, that is equally lonely but adds tragedy, like knowing there were other people in the world, but each in permanent, solitary confinement. Either way, reflecting on the night sky can induce what might be called the lonely sublime. We gaze at billions of stars and realize no help or company is coming from out there, at least not in any foreseeable time frame. Just us and our planet, a tiny oasis in a vast desert. This perspective can unite humans. All our divisions become trivial if we are one-of-a-kind beings in a lifeless sea. Everyone you love, every conflict, every hero and coward lived on what Sagan called a mote of dust suspended in a sunbeam. There is nowhere else, at least in the near future, to migrate to. This underscores the fragility and preciousness of life and the absurd pettiness of our divisions. Philosopher Toby Ord calls our time the precipice. We stand at a cliff's edge where one step wrong means oblivion, one step right means a vast future. How often in history could people say their actions might literally affect billions of years to come? That gives powerful context to seemingly mundane decisions. How we regulate artificial intelligence, what energy sources we invest in, whether we maintain global cooperation or fragment into conflict. There is almost a dramatic heroism to this perspective. Humanity collectively is like the protagonist in a grand story, facing trials that will lead either to triumph, survival and flourishing among the stars, or to tragedy, self-destruction, like countless hypothetical civilizations before us. This narrative can inspire unity and purpose, though it can also induce fear. The key is channeling that awareness into action rather than paralysis. If the Great Filter lies ahead, can we do anything about it? The NASA paper by Jiang and colleagues argues yes. They call for what they describe as a necessary period of introspection, a deliberate effort to assess our trajectory and mitigate threats before they overwhelm us. Specific actions include reducing nuclear arsenals further. The 80% reduction from Cold War peaks is encouraging, but 12,000 warheads remain more than enough to end civilization. Continued disarmament and risk reduction measures matter. Strengthening biosecurity. This means better global surveillance networks for emerging pathogens, rapid vaccine development platforms, and careful oversight of gain-of-function research that could accidentally create dangerous pathogens. Developing artificial intelligence carefully. The statement signed by AI leaders in 2023, treating AI extinction risk as a global priority alongside pandemics and nuclear war, suggests that even those building these systems recognize the need for caution. Alignment research, safety protocols, and perhaps international coordination on AI development all matter. Addressing climate change. Transitioning away from fossil fuels is extraordinarily difficult, but not impossible. Every fraction of a degree of warming avoided reduces the risk of cascading failures. Becoming multiplanetary. Perhaps the most direct way to reduce extinction risk is to establish self-sustaining populations beyond Earth. NASA plans human moon landings through the Artemis program, and discussions of crewed Mars missions in the 2040s continue. If humanity had viable settlements on Mars, A catastrophe that destroyed Earth would not end our species entirely. Building institutions that think long-term, projects like seed vaults, knowledge archives, and 10,000-year clocks represent efforts to treat our civilization as something worth preserving over geological timescales. This is a shift from the short-termism that dominates most political and economic thinking. Each of these represents a conscious effort to navigate the minefield rather than stumbling blindly. Let me return to the counterintuitive insight that frames so much of this discussion. Every time SETI reports another year of silence, every time a Mars mission finds no trace of ancient microbes, every time an exoplanet survey detects no biosignatures, these results, while disappointing to our curiosity, might actually be good news for our survival. An empty universe suggests the great filter is behind us. The silence tells us that we might have already won the cosmic lottery. The odds were unimaginably against us, but here we are. If this interpretation is correct, it means the road ahead, while difficult, is not necessarily fatal. We would be the rare survivors in a universe where almost nothing else made it this far. That is a burden, a responsibility, but it is also a form of hope. Conversely, if we began finding life everywhere, microbes on Mars, biosignatures on multiple exoplanets, signs of ancient bacteria in asteroid samples, we would need to worry. It would suggest life is easy. And if life is easy but no one else is out there building radio telescopes, then something terrible must be happening to stop them. The silence in this strange framework is a gift, one we should not take for granted. The progression of human understanding on these questions follows a fascinating arc. Enrico Fermi asked his question in 1950, planting the seed. Frank Drake wrote his equation in 1961, organizing our ignorance. The Hart-Tipler arguments in the 1970s and 1980s sharpened the paradox. David Brin named the Great Silence in 1983. Robin Hanson coined the Great Filter in 1996. Nick Bostrom explored its implications in 2008. By 2022, NASA scientists were using the framework to analyze real-world policy. Each step built on the previous. Each generation of thinkers added nuance. What began as a lunchtime musing at Los Alamos became a lens through which we might understand our place in the cosmos and our responsibilities to the future. The scientists and philosophers who have worked on this question deserve recognition. Their willingness to grapple with uncomfortable possibilities, that we might be alone, that we might be doomed, that finding life might be bad news, represents intellectual courage. I want to share something personal before we close. When I first encountered the Great Filter concept, I felt a chill, a mix of loneliness and urgency that I've not shaken since. I was lying under a starry sky, countless stars above, yet an eerie silence surrounding me. Civilizations flash and fade so fast that none are shining out there now. That thought struck me that night. That feeling has stayed with me. It has shaped how I think about what matters. I used to be enthralled by SETI. I wanted desperately to hear that alien signal, to know we were not alone. When I learned about the Great Filter, my perspective shifted. I realized that if we did hear something, it might mean our days are numbered. Now, every time there is news about possible life detected somewhere, I feel a conflicted knot, part excitement, part fear of what it implies. The more I learn about the scale of what is out there, the more I realize how small our certainties are. And honestly, I find that beautiful, not troubling. There is wonder in mystery. There is meaning in the questions themselves, even when answers remain beyond reach. Someone once asked me whether I feel optimistic or pessimistic about our future, given all these existential risks. Honestly, I feel both, and each day, one or the other dominates. I remember a line I read once: "Optimism and pessimism are self-fulfilling prophecies. If we assume doom, we will likely do nothing and get doom. If we assume a great future is possible, we work toward it and maybe achieve it." So I choose cautious optimism, not because I am sure we will make it, but because it gives us the best fighting chance. That choice, to me, is an act of will, perhaps the most important one of our era. To truly appreciate how unlikely our existence might be, let me walk you through Earth's timeline compressed into a 24-hour clock. If Earth's formation 4.54 billion years ago occurred at midnight, what would we see as the hours progressed? The earliest signs of life, simple single-celled organisms, appear around 5 a.m. For the next 15 hours, almost nothing changes visibly, and single-celled life dominates the planet. Simple prokaryotes, cells without nuclei, are the only inhabitants, with billions of years passing in that microbial monotony. Complex cells with nuclei, eukaryotes, finally emerge around 3 p.m., still single-celled, but a crucial step. Multicellular animals do not appear until approximately 8:30 p.m. After roughly 20 hours of life's existence, complexity finally takes hold. The Cambrian explosion, that sudden flowering of diverse animal life, occurs around 9 p.m. The dinosaurs go extinct at 11:40 p.m., just 20 minutes before midnight. Modern humans appear at 11:59:30 p.m., the last 30 seconds of the entire day. Our industrial technological era, the time since we split the atom and built radios and rockets, occupies the final fraction of a second. If you blinked, you would miss human civilization entirely. This illustration highlights several points relevant to the Great Filter. First, the path from microbes to intelligence was long and tortuous, spanning billions of years with several huge leaps that took enormous time to achieve, and each of those leaps could have failed to occur at all. Second, humanity's technological phase is extremely new and potentially fleeting in geological terms. We have existed as a technological species for an eye blink, and if the Great Filter ahead is real, our current high-tech civilization might be a transient spark that quickly fades, relative to planetary or cosmic timescales. Third, there were 5 mass extinctions during that timeline, moments when the majority of species on Earth perished. The Permian-Triassic extinction, 250 million years ago, wiped out approximately 96% of marine species and 70% of land species. Earth's biosphere is resilient, but one can imagine alternate timelines where complex life never recovered. Natural filters exist even without technological self-destruction. We stand on the shoulders of survivors, an unbroken chain stretching back billions of years through extinctions and catastrophes and bottlenecks. Every ancestor in your lineage survived long enough to reproduce. Every species in your ancestral lineage avoided extinction long enough to give rise to the next. The probability of any specific lineage making it through that gauntlet is vanishingly small. That we exist at all represents one of the most improbable chains of events conceivable. Let me give you a concrete example of how close humanity has come to triggering the Great Filter through nuclear war. The Doomsday Clock is a symbolic timepiece maintained by the Bulletin of the Atomic Scientists since 1947, representing how close humanity is to catastrophic destruction, with midnight symbolizing annihilation. In 2024, the Doomsday Clock was set to 90 seconds to midnight, the closest it has ever been due to nuclear tensions and other risks. The closest we actually came to nuclear war was not in our present, but in October 1962, during the Cuban Missile Crisis. For 13 days, the United States and the Soviet Union stood on the brink of nuclear exchange over Soviet missiles placed in Cuba. President Kennedy and Premier Khrushchev engaged in a tense standoff while the world held its breath. What most people did not know at the time, and what only emerged decades later, was how much closer we came than even the leaders realized. On October 27, 1962, a Soviet submarine designated B-59 was being depth-charged by American destroyers near Cuba. The submarine had been out of contact with Moscow and did not know whether war had already begun. The captain, Valentin Savitsky, ordered the arming of a nuclear torpedo. On most Soviet submarines, the captain could launch alone, but B-59 was special because it carried a nuclear weapon, and protocol required agreement from 3 officers. Captain Savitsky wanted to launch. The political officer agreed. 2 votes for nuclear war. The 3rd officer, Vasily Arkhipov, refused. Arkhipov argued against launching, insisting they surface and contact Moscow first. After intense argument in the sweltering submarine, Arkhipov prevailed, and the submarine surfaced. Had Arkhipov not been on that submarine, or had he agreed with his colleagues, a nuclear torpedo would have struck the American fleet. The American response would have been immediate and overwhelming, and full-scale nuclear war between superpowers would likely have followed. The fate of human civilization may have rested on one man's judgment in a cramped submarine with no air conditioning and no contact with the outside world. This is what the Great Filter might look like in practice, not an inevitable doom, but a series of moments where the wrong decision by the wrong person at the wrong time could end everything. We have been lucky so far. How many more such moments will we face? And how long can luck hold? Let me add more context to the exponential growth equation we discussed earlier. Thomas Malthus, writing in 1798, warned that human population grows exponentially while food production grows only linearly. And Malthus predicted that population would inevitably outstrip resources, leading to famine, disease, and societal collapse. For 2 centuries, Malthus appeared to be wrong. Technological advances, agricultural modernization, mechanized farming, synthetic fertilizers allowed food production to keep pace with population growth, and the predicted collapse never arrived. The Malthusian shadow has not disappeared. It has merely been deferred. World population reached 1 billion around 1800. Reaching 2 billion took 123 years. In 1927. Just 33 years later, we hit 3 billion in 1960. 4 billion came in 1974, only 14 years. 5 billion in 1987, 13 years. 6 billion in 1999, 12 years. 7 billion in 2011, 12 years. 8 billion in 2022, 11 years. The intervals between billions shortened dramatically as exponential growth accelerated. Only in recent decades has the growth rate begun to slow. By the mid-2000s and 60s, projections suggest global population might peak around 10 billion, though significant uncertainty remains. And here is the deeper concern. Not just the number of people matters, but the resource consumption per person. As developing nations industrialize and living standards rise, which is generally a good thing, total resource demand accelerates even faster than population. Each year, humanity emits roughly 40 billion tons of carbon dioxide. We are depleting aquifers, eroding topsoil, acidifying oceans, and driving species to extinction at rates not seen since the age of dinosaurs. The question is whether technology can continue to outpace resource constraints indefinitely, or whether we are simply deferring a reckoning. The Great Filter might not be a single catastrophic event, but a gradual overshoot followed by collapse, a slow-motion version of bacteria filling a bottle and then crashing when they exhaust their nutrient supply. In 1990, the Voyager 1 spacecraft, then 3.7 billion miles from Earth, turned its camera backward and captured an image of our planet. Earth appeared as a tiny blue speck, barely visible against the vastness of space, less than a single pixel in the frame. Carl Sagan, who had requested the photograph, wrote perhaps the most famous passage in space literature about what it revealed. Every human who ever lived on that mote of dust. Every war, every triumph, every act of love or hatred occurred on that pale blue dot suspended in a sunbeam. All of human history, all of human potential exists on a world so small it is nearly invisible from the outer reaches of our own solar system. From the Great Filter perspective, this image is both humbling and terrifying. Humbling because it shows our insignificance in spatial terms. We occupy a tiny world, orbiting an ordinary star in an ordinary galaxy among trillions of galaxies. Terrifying because it shows our vulnerability. Everything we are, everything we might become, exists in one location, and a single asteroid, a single gamma-ray burst, a single self-inflicted catastrophe, any of these could erase that pixel of light. If the Great Filter is ahead of us, it is as if an invisible glass ceiling exists. We can send radio waves maybe, and we can dream of the stars. Travel and colonization are always cut short, and every civilization is born inside a room with high walls. They can throw a ball up and watch it fall back, but they can never climb out, and eventually they perish inside the room. The Fermi paradox is telling us that across the universe, this might be everyone's fate. Billions of lonely, silent dots, each species trapped on its pale blue world, doomed to die there, never meeting others. That image, that lonely mote of dust, is haunting, and it is exactly what the night sky looks like right now. Before we conclude, I should mention one alternative explanation for the Great Silence that is not strictly a Great Filter scenario, but overlaps with it in troubling ways. The dark forest hypothesis, popularized by science fiction author Liu Cixin, suggests that the universe is not empty, but dangerous. Advanced civilizations exist, but they remain silent because revealing yourself is fatal. The logic runs like this. Any civilization that broadcasts its presence might attract the attention of a more advanced civilization that views all others as potential threats. In a universe with limited resources and no way to verify peaceful intentions across interstellar distances, the safest strategy is to eliminate potential competitors before they become dangerous. And the safest way to avoid being eliminated is to stay hidden. In this scenario, the Great Silence is not because civilizations are rare or because they destroy themselves. Civilizations are hiding because the universe is a dark forest full of hunters, and anyone who makes noise gets shot. This is chilling in a different way. It suggests that even if we survive our technological adolescence, even if we avoid nuclear war and engineered pandemics and AI catastrophe, we might still face doom the moment we become detectable to others. Our radio and television signals have been leaking into space for roughly a century, reaching about 100 light-years, touching thousands of star systems. If something is listening, it may already know we are here. This hypothesis is speculative and unprovable with current evidence. It represents another possible filter, not internal self-destruction, but external predation. The universe might be hostile in ways we have not yet experienced. How has humanity responded to the recognition of existential risks? In some ways, encouragingly. The nuclear arsenals that peaked at 70,300 warheads in 1986 have been reduced to approximately 12,300. Treaties like START and New START, despite tensions, have constrained the worst excesses of the arms race. The Cuban Missile Crisis and near misses like the 1983 Soviet nuclear false alarm have taught hard lessons about the need for communication and restraint. The Montreal Protocol of 1987 successfully addressed the ozone hole by phasing out chlorofluorocarbons, standing as perhaps the clearest example of global cooperation averting an environmental catastrophe. The Paris Agreement of 2015, while imperfect and insufficient, represents nearly universal acknowledgement that climate change requires coordinated action. Almost every nation on Earth signed it. The rapid development of COVID-19 vaccines, from viral genome to approved vaccines in less than a year, demonstrated remarkable scientific capability. And if we can maintain and enhance that capacity, we may be able to respond to even deadlier pandemics. NASA's DART mission proved we can deflect asteroids. The technology exists, and given enough warning, we can protect Earth from cosmic impacts. Institutions like the Future of Humanity Institute at Oxford, the Centre for the Study of Existential Risk at Cambridge, and the Global Challenges Foundation are dedicating serious intellectual resources to understanding and mitigating existential threats. In other ways, the response has been inadequate. Carbon emissions continue to rise in absolute terms. The Paris Agreement's targets are not being met. Climate action remains far behind what science says is necessary. Artificial intelligence development is proceeding at breakneck pace with inadequate governance frameworks. The race for AI supremacy among nations may be prioritizing capability over safety. Biosecurity remains underfunded relative to the risk. The COVID-19 pandemic revealed how unprepared the world was for a moderately lethal pathogen, let alone something engineered to be maximally dangerous. Nuclear weapons still exist in quantities sufficient to end civilization, and the breakdown of arms control agreements in recent years is concerning. The honest assessment is that humanity is aware of the dangers but has not yet risen to meet them adequately. We are walking through the minefield with our eyes half open, better than blindfolded, but not good enough. Let me offer one more reflection before we close. Throughout most of human history, our ancestors could not have conceived of extinction as a realistic possibility. Natural disasters, wars, plagues, these were local or regional catastrophes, terrible but survivable as a species. Someone, somewhere, would continue. That changed in 1945. For the first time, humans possessed the power to end civilization entirely, and within decades, we possessed the power to render our planet uninhabitable for complex life. This is unprecedented. No previous generation faced the possibility that their decisions could terminate the human story forever. No previous generation had both the capability to destroy everything and the knowledge to understand what they were risking. We are the first to bear this weight, and we may be among the last who have the chance to set things right before it is too late. Philosopher Derek Parfit called our time the hinge of history, a period when actions matter more than at any other time, because they shape whether there will be a future at all. If we succeed, if we navigate the next century or two without triggering catastrophe, if we become multiplanetary, if we establish safeguards that persist, then the vast majority of human lives and human achievements will lie in the future, not the past. Trillions of people might yet be born. Civilizations might flourish across solar systems. The story of conscious life in this universe could be just beginning. If we fail, there may be no one to remember that we ever tried. The stakes could not be higher, and the decisions we make now in this generation may determine everything that follows. Let me tell you more about the most comprehensive search for extraterrestrial intelligence ever undertaken. The Breakthrough Listen initiative, funded by Russian-Israeli billionaire Yuri Milner with $100 million, began in 2015. The project uses some of the world's most powerful radio telescopes, including the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, to scan the cosmos for artificial signals. Breakthrough Listen has scanned thousands of nearby stars across billions of radio frequencies. The sensitivity is remarkable, with instruments that can detect Earth-level radio transmissions from stars dozens of light-years away. If a civilization similar to ours existed around any of the nearest 1,000 stars and was broadcasting at our power levels, Breakthrough Listen would likely hear it. The results, as of 2026, are consistent with the Great Silence. No confirmed artificial signals have been detected. Several candidate signals have been identified over the years, each generating excitement before being explained by natural phenomena or human interference. The most notable was the 2020 signal from the direction of Proxima Centauri, designated BLC1. This narrow-band signal at 982 MHz initially passed multiple filters designed to eliminate false positives. For months, scientists worked to determine its origin, and by 2021, detailed analysis revealed the signal was almost certainly terrestrial interference that had somehow mimicked the characteristics of an artificial extraterrestrial transmission. This episode illustrated both the promise and the challenge of SETI. Our instruments are powerful enough to detect faint signals across interstellar distances, but our own technology generates enormous radio noise that can create false alarms. Every microwave oven, every satellite, every piece of electronic equipment contributes to the cacophony. Breakthrough Listen has also searched for other technosignatures. The project has looked for laser pulses that might indicate optical communication between civilizations, and the initiative has analyzed the light curves of stars for anomalies that might suggest megastructures like Dyson spheres partially blocking starlight. Perhaps the most famous such anomaly was Tabby's star, formerly designated KIC 8462852. This star showed bizarre dimming patterns that some speculated could be caused by alien structures orbiting it. Detailed observations eventually attributed the dimming to dust clouds, not alien construction. But the investigation demonstrated how SETI has grown beyond simply listening for radio signals to searching for physical evidence of engineering on astronomical scales. The continued silence after decades of searching carries information. It tells us that if technological civilizations exist in our galactic neighborhood, they are either not broadcasting at detectable levels, or not broadcasting at all, or they do not exist. The breakthrough. Listen team continues their work. The search is far from complete because our galaxy alone contains hundreds of billions of stars, and we have examined only a tiny fraction. With each year of silence, the statistical weight shifts slightly toward the conclusion that detectable civilizations are rare, perhaps extremely rare. Let me provide a more detailed picture of how researchers assess the various threats that might constitute a future great filter. Organizations like the Future of Humanity Institute at Oxford, the Centre for the Study of Existential Risk at Cambridge, and the Global Challenges Foundation have attempted to quantify these risks. While precise probabilities are impossible to determine, their estimates provide a framework for thinking about our situation. One 2020 estimate put the overall chance of human extinction in the next century at roughly 1 in 6, approximately 17%, when aggregating all major risks. This figure is not precisely derivable, but it reflects serious expert assessment that the risk is far from negligible. For nuclear war leading to civilizational collapse, estimates typically range from 1 to 3% over the next century, accounting for both deliberate conflict and accidental launches due to technical failures or misperceptions. For bioengineered pandemics, estimates run from 3 to 5%, with the combination of advancing biotechnology and the difficulty of controlling dangerous pathogens making this a growing concern. For unaligned artificial intelligence leading to catastrophe, estimates range from 5 to 15%. The uncertainty here is enormous because we are projecting capabilities and risks for technologies that do not yet exist. But even the lower estimates represent unacceptable danger. For climate change-triggered collapse, estimates typically fall in the range of 1 to 3% for true civilizational collapse, though lower-level catastrophes affecting billions of people are considerably more likely. These risks are not independent. A severe climate crisis could heighten resource conflicts, increasing the probability of nuclear war. A major pandemic could destabilize governments, making nuclear security less reliable. Economic collapse from any cause could undermine our ability to respond to other threats. The researchers who work on these problems emphasize that the numbers are illustrative rather than precise. What matters is the order of magnitude. We are not talking about risks of 1 in a million, which could be safely ignored. We are talking about risks of 1 in 10, or 1 in 20, or 1 in 6 over the span of a century. If you faced a 1 in 6 chance of catastrophe from any other cause, getting on an airplane, crossing a street, you would consider it unacceptably dangerous. This is roughly the situation facing human civilization as a whole, according to careful expert assessment. Earlier, I mentioned the Kardashev scale briefly. Let me expand on what it means and why it matters for understanding the Great Filter. Soviet astronomer Nikolai Kardashev proposed his classification system in 1964 as a way to categorize civilizations by their energy consumption. The scale has since become a standard framework for discussing the potential development of technological civilizations. A Type 1 civilization harnesses all the energy available on its home planet, roughly the amount of solar energy that falls on the planet's surface. For Earth, this is approximately 1.74 times 10 to the 17th watts continuously. Kardashev originally defined Type 1 as roughly 4 times 10 to the 12th watts, representing total planetary energy availability, including internal heat and other sources. Humanity currently consumes about 1.8 times 10 to the 13th watts, 18 terawatts. By some calculations, this puts us at roughly 0.7 on the Kardashev scale, approaching but not yet achieving Type 1 status. A Type 2 civilization harnesses the total energy output of its host star. For a star like our Sun, this is approximately 3.8 times 10 to the 26th watts, roughly 20 billion times more energy than a Type 1 civilization commands. Such a civilization might construct a Dyson sphere or Dyson swarm, a vast collection of structures surrounding the star to capture its output. A Type 3 civilization harnesses the energy of an entire galaxy. The Milky Way's total luminosity is approximately 4 times 10 to the 37th watts, and a Type 3 civilization would command roughly 100 billion times more energy than Type 2. The gaps between these levels are staggering. Moving from Type 1 to Type 2 requires increasing energy use by a factor of roughly 20 billion. Moving from Type 2 to Type 3 requires another factor of 100 billion. Why does this matter for the Great Filter? First, these energy levels have implications for detectability. A Type 2 civilization would significantly alter its star's light output, because capturing most of a star's energy means the star's visible light would dim while infrared radiation from waste heat would increase. Astronomers have searched for stars with these signatures and found none that cannot be explained by natural phenomena. A Type 3 civilization would transform an entire galaxy's appearance. If such civilizations existed, we would expect to see galaxies with unusual spectral properties, reduced visible output, enhanced infrared. Surveys of distant galaxies have found nothing convincingly artificial. Second, the energy levels suggest why advancement might be dangerous. Managing Type 1 energy levels means managing power sufficient to alter planetary climate. Managing Type 2 energy levels means managing power sufficient to sterilize planets or destabilize solar systems. Each step up the Kardashev scale brings capabilities for creation and destruction on vaster scales. The Great Filter might operate at the transition from Type 0.7, where we are now, to Type 1. Managing planetary-scale energy without destroying the planetary environment or triggering nuclear war might be extraordinarily difficult, and most civilizations might fail at this transition. Alternatively, the filter might operate at higher levels. Perhaps achieving Type 2 requires millennia of coordinated development, and most civilizations collapse into conflict or stagnation before reaching it. The absence of visible Type 2 or Type 3 civilizations anywhere in our past light cone, despite billions of years of opportunity, is powerful evidence that something stops civilizations before they reach these stages. That something is the Great Filter. Earth has experienced 5 major mass extinctions in its history. Each offers lessons relevant to the Great Filter. The Ordovician-Silurian extinction, approximately 445 million years ago, killed an estimated 85% of marine species. The cause was likely glaciation as the supercontinent Gondwana drifted over the South Pole, drastically lowering sea levels and temperatures. The late Devonian extinction, approximately 375 million years ago, eliminated roughly 75% of species over an extended period. The causes remain debated, but may have involved changes in ocean chemistry and oxygen levels. The Permian-Triassic extinction, approximately 252 million years ago, was the most severe, the Great Dying, that eliminated roughly 96% of marine species and 70% of land vertebrate species. Massive volcanic eruptions in what is now Siberia likely triggered runaway climate change and ocean acidification. The Triassic-Jurassic extinction, approximately 201 million years ago, killed roughly 80% of species. Again, massive volcanism appears responsible. The Cretaceous-Paleogene extinction, 66 million years ago, ended the age of dinosaurs. An asteroid impact at what is now the Yucatan Peninsula, combined with massive volcanism in India, caused global fires, impact winter, and ecological collapse, and roughly 76% of species vanished. What can these events teach us about the Great Filter? First, extinction is the norm, not the exception. The vast majority of all species that have ever lived are gone. Survival is statistically unusual. Second, external catastrophes, asteroids, volcanic supereruptions, can strike without warning and cause devastation on scales that dwarf anything in human experience. These are natural filters that have operated throughout Earth's history. Third, environmental instability, climate change, ocean acidification, oxygen depletion can trigger cascading collapses that eliminate most complex life even without a single dramatic event. Fourth, recovery is possible but slow. After the Permian extinction, it took roughly 10 million years for biodiversity to recover. After the Cretaceous extinction, it took millions of years for large animals to diversify again. If human civilization collapses, there may not be a second chance on timescales relevant to our discussion. Fifth, and most importantly, none of these extinctions eliminated all life. Microbes persisted through everything. Simple organisms endured. Complex, intelligent life is far more fragile. The Great Filter might not be the extinction of life itself, but the extinction of the particular conditions and organisms that lead to intelligence and technology. Astronauts who have seen Earth from space often describe a shift in perspective called the overview effect. They report that seeing our planet as a single fragile sphere floating in the darkness transforms their understanding of humanity's situation. Astronaut Edgar Mitchell, who walked on the Moon during Apollo 14, described it this way: "You develop an instant global consciousness. a people orientation, an intense dissatisfaction with the state of the world, and a compulsion to do something about it. Astronaut Ron Garan said, "When you go around the Earth in an hour and a half, you see that the sun rises and sets 16 times. You notice that there are no borders from space." This perspective shift is relevant to the Great Filter for several reasons. First, it reveals the unity and vulnerability of our situation. From space, the borders and conflicts that divide humanity appear artificial and trivial. The atmosphere that sustains all life appears as a thin, fragile shell. The planet appears as the one lifeboat we have. Second, it suggests what might be needed to navigate existential risks successfully. The threats we face, nuclear war, climate change, pandemics, AI, are global problems that require global solutions. They cannot be solved by any single nation acting alone. The overview effect, if it could be experienced more widely, might foster the kind of planetary consciousness necessary for effective collective action. Third, it connects to the ultimate ambition that might follow passing the Great Filter. If humanity survives and expands into space, we will carry that perspective with us. We will become a multiplanetary species, no longer confined to a single fragile world. The overview effect, in a sense, points toward the future we might achieve if we make the right choices. The astronauts who have experienced this perspective describe it as both humbling and empowering. Humbling because it reveals how small and vulnerable we are. Empowering because it clarifies what matters and what we must do. Before I offer closing thoughts, I want to pause and invite you to reflect. Think about what you have learned tonight. The vastness of the cosmos, billions of galaxies, trillions of stars, numbers that dwarf human comprehension. The silence that confronts us, no signals, no artifacts, no evidence that anyone else has achieved what we are trying to achieve. The Great Filter, some barrier so deadly that it stops almost everything from reaching spacefaring status. Now ask yourself, where do you think the Great Filter lies? Do you believe the hardest steps are behind us? That the origin of life or the emergence of intelligence was so improbable that we are genuinely alone in the observable universe? Or do you suspect the filter lies ahead? That the challenges of our current technological era, nuclear weapons, climate change, artificial intelligence, engineered pathogens, represent the same crisis that has claimed every other civilization before us? What would it mean for how you live your life if the filter is behind us? If we are truly the winners of a cosmic lottery, carrying the only flame of consciousness in an otherwise dark universe? What would it mean if the filter is ahead? If the decisions our generation makes will determine whether that flame continues or goes out forever? There is no way to know for certain which scenario is true. The evidence is ambiguous. The silence could mean we are rare, or it could mean no one survives. But here is what I believe. The uncertainty itself is a call to action. If the filter might be ahead, we have every reason to work toward avoiding it. If the filter is behind us, we have every reason to honor our improbable existence by building something worthy of it. Either way, we should act as if our choices matter, because they do. We have journeyed together through one of the most profound questions humans can ask. Why is the universe silent? Where is everybody? What barrier claims civilizations before they can reach the stars? The Great Filter, This theoretical explanation for the cosmic silence forces us to confront uncomfortable possibilities. Either we are astonishingly rare, the survivors of nearly impossible odds, or we face a challenge that has defeated every other civilization that reached our stage. The statistics are stark: roughly 10 to the 23rd stars in the observable universe, billions of years for life to arise and spread. Silence. Something is stopping civilizations from becoming visible on galactic scales. Something is preventing the cosmos from being filled with intelligence and activity and signs of engineering. That something is the great filter. We are either past it or approaching it. I have shared with you the equations that govern both our power and our peril. E equals mc squared, which gives us nuclear weapons. The exponential growth equation, which describes both our explosive population increase and the chain reactions that could end us. The Drake equation, which organizes our ignorance about life in the cosmos. The escape velocity formula, which represents the barrier between planetary confinement and interstellar possibility. I have shared the historical arc from Fermi's question in 1950 through Drake's equation in 1961, Hansen's great filter in 1996, Bostrom's analysis in 2008, and the NASA paper in 2022. Each generation of thinkers has added depth to our understanding of what we face. I have shared the current frontiers: the James Webb Space Telescope searching for biosignatures, the Perseverance rover caching samples on Mars, the SETI initiatives scanning the sky, the missions preparing to explore the ocean moons of Jupiter and Saturn. I have shared the risks: nuclear war, engineered pandemics, artificial intelligence, climate change, that might constitute the great filter if it lies ahead of us. The silent stars above us tonight carry a message. They tell us we are alone, or nearly so. They tell us that whatever stopped all the others might be waiting for us. They also tell us that if we are aware of the danger, perhaps we can be the exception. We are approaching the barrier that kills all civilizations. Let us be the ones who break through. Thank you for joining me on this exploration. If this content resonated with you, please subscribe and share it with others who might find value in these questions. Sleep well tonight under the silent stars. May we prove worthy of the cosmic lottery we appear to have won. Good night. We have covered immense ground tonight. We began with the silent night sky and the terrifying possibility it conceals, that a great barrier awaits every advanced civilization, and we may be fast approaching it. We explored the scale of the cosmos, hundreds of billions of stars in our Milky Way galaxy alone, trillions of galaxies in the observable universe, 10 times more stars than grains of sand on all of Earth's beaches. We saw how the mathematics of probability screams that we should not be alone, and yet, everywhere we look, we see nothing. We examined the Drake equation and the chain of hurdles any civilization must clear. We considered candidate filters in our past: the origin of life, the emergence of complex cells, the development of intelligence, any of which might have been nearly impossible, making our existence a cosmic fluke. We confronted the terrifying possibility that the great filter lies ahead. Nuclear war, engineered pandemics, artificial intelligence misaligned with human values, climate collapse. Each represents a way our civilization could end, perhaps the same way every other civilization has ended before us. We learned the equations that govern these fates. E equals mc squared, which gives us both stellar energy and nuclear annihilation. The exponential growth equation, which describes both population expansion and chain reactions. The kinetic energy formula, which quantifies the destructive power of asteroid impacts. The escape velocity equation, which represents the price of admission to the cosmos. We grappled with the counterintuitive truth that finding alien life would be bad news, that an empty universe might be our greatest hope. We explored the limits of scientific explanation, acknowledging that some questions may sit beyond the reach of telescopes and equations. Through it all, the Great Filter has served as both warning and call to action. It tells us that whatever killed or stopped all those other potential civilizations might be waiting for us too. It also tells us that if we are aware of the danger, perhaps we can avoid it. Humanity stands at a crossroads. We are developing capabilities, artificial intelligence, genetic engineering, energy systems that could either secure a flourishing future or trigger catastrophe. The decisions we make in the coming decades may determine whether intelligent life continues in this corner of the universe or vanishes like so many hypothetical civilizations before us. The Great Filter, whatever it is, must be almost perfectly lethal, and yet here we are, contemplating it. That we can even have this conversation means we have already beaten enormous odds. The next time you look up at the night sky, consider what you are seeing. Billions of stars, countless worlds, silence. That silence might be telling us something important, that we are rare, that we are precious, that we carry a responsibility we never asked for, but cannot escape. Whether we are the first civilization to reach this point, or the only civilization that will ever reach it, the stakes could not be higher. Thank you for staying with me through this exploration of one of the most profound questions we can ask about our place in the cosmos. We have traveled from Enrico Fermi's lunchtime question in 1950 to the cutting-edge searches of the James Webb Space Telescope. We have examined equations that describe both the power of stars and the devastation of nuclear weapons. We have confronted the strange truth that finding alien life might be the worst news we could receive. Through it all, one theme has emerged. We live in an extraordinary time. A time when our actions might shape not just decades or centuries, but the entire future of conscious life in our corner of the universe. The Great Filter, the barrier that kills all civilizations, may lie in our past, making us the rare survivors of an almost impossible gauntlet. Or it may lie ahead, waiting to claim us as it has claimed, perhaps, every other civilization that reached this point. The silent stars offer no answer, only a question. What will we do with the time we have? If you found value in this exploration, please consider subscribing and sharing this video. Conversations like this one matter. They shape how we think about our future and what we choose to do with it. The next time you look up at the night sky, remember what you have learned tonight. Those silent stars, beautiful and distant, are also a warning, a reminder that the universe may be far more empty and dangerous than our ancestors imagined. They are also an invitation, a call to be the exception, to prove that intelligence can survive its own power, to carry the light of consciousness as far as it can go. Sleep well tonight, under a sky full of silent stars. Tomorrow, perhaps, help build a future worthy of the improbable gift of existence. We are approaching the barrier that kills all civilizations. Let us be the ones who break through.